Okay, so I want to spend the rest of the today talking about continuous valued Markov random fields, starting with Gaussian Markov random fields. And of course, there is a reason why I, invest your and my time in this. And the reason is that these have seen a steep career. So for, let's say, the last, well, 7 years or so, not true. So um, the the first member of this family that made its appearance in image analysis was the random walker, and this was a particular seeded segmentation algorithm with nice theoretical properties, but a bit slow in practice. So it was not used excessively, and more flexible versions of Gaussian Markov random fields have now come to the fore that are in some applications the current state of the art. And that, even though these continuous valued MRFs have appeared on the scene uh, in image analysis at least later than the discrete ones. So they are of much current interest. And I will build this topic up systematically by first talking about Gaussian Markov random fields, and then intrinsic Gaussian Markov random fields, and the random walker, and finally regression tree fields. So Gaussian Markov random fields have been known to statisticians for a long time. In many respects, the easiest thing you can do in statistics is assume a normal distribution, and such high-dimensional Gaussians have been used for a long time to infer, let's say, genetic networks and such from bioinformatics data. So they are specified very conveniently for zero mean. The probability of X is proportional to the determinant of the precision matrix Q taken to the power of a half times e to the minus 1/2 X transpose QX. And well, if we work in image analysis, we have images. So let's say X for us is a vectorized image. An image where we've read out the pixels column by column and appended them into a single vector. Q is called the precision matrix or the concentration matrix. And however you call it, it's the inverse of the covariance matrix. And there's a theorem, so it's known for distributions of any type, that if the partial correlation between two random variables is 0, that in that case the corresponding element of the precision matrix is 0. But for Gaussians, one can make an even stronger statement, namely that an element ij of the precision matrix being 0 is equivalent to xi being conditionally independent of xj, given all other points, or given all other random variables. People hear this on YouTube, they must think we live in a really criminal neighborhood. But it's just that we're next to the fire station. It's okay, really. Okay. if you want to admit a mean mu, then you get something very similar. You just have in your quadratic expression x minus mu transpose. So you just replace x by x minus mu. So we can say that the collection of random variables x is a Gaussian Markov random field with respect to a graph H comprising vertices. And well, actually now I can write a normal graph G because we will only have pairwise interactions. With a precision matrix Q. Okay, let me write the expression with the mean just so you've seen it once. So here with mean mu and with precision matrix Q, if the probability is a multivariate Gaussian, and if Qij, if an element of the precision matrix being non-zero implies that we have an edge between I and j in our set of edges that constitute our graph. And we can then ask about the conditional density. If I partition my set of random variables such that V is composed or decomposed into A and B, which must be non-overlapping. Excuse me, which must be non-overlapping. So A intersected with B is the empty set. Then I can partition correspondingly the random variables and the mean and also the precision matrix. If I'm now asking for about the distribution of my set of random variables xa conditioning on xb, then this is still a Gaussian Markov random field with respect to a subgraph GA that comprises only the vertices in A and only edges of which both incident vertices are also in A. So EA is the set of edges ij where I is in A and J is in A, and I and J must be different. So this is still the Gaussian Markov random field with parameters mu A conditioned on B and Q A conditioned on B. And you can show that QA conditioned on B is just QAA. And if you want the proof, you can look, for example, in the nice textbook by Lauritsen, or in a paper by Havard-Rue, or in the recordings from the pattern recognition lecture. There's also a lecture on Gaussian processes where I think I've also shown the proof. Okay, so let's look at the conditional mean, mu A conditioned on B. We can find it as follows. We can minimize over X on the subset A this expression. And the only thing that is not given here is the XA. So everything else is known, or is assumed known. And then you can multiply this expression out and differentiate with respect to XA. And to find extremum, set this derivative to 0. And you then find the following, that QAA times XA minus mu A is minus QAB times XB minus mu B. And we want to solve this with respect to XA. And by the condition that you've seen above, for Gaussian Markov random fields, this is typically sparse. So at least if you design the model, then you design it specifically in a way so as to have a sparse network with a precision matrix that has many zeros. And in any case, it's a linear system of equations, but in most cases this is going to be a sparse system of linear equations. So it being a system of linear equations tells you what is going to be the computational complexity, but it being sparse means it can be better than that in practice. So better than this worst case complexity. So if we solve this expression here, solving for XA gives us the conditional mean, which for Gaussian is also the mode, so the peak of the distribution. Mu A conditioned on B. So formally, you can write this using this matrix inverse. So I forgot the mu A. Formally, you can write it using this matrix inverse, but this is not how you're going to compute it in the real world. So if QAA is sparse, then QAA to the -1 is going to be dense, and hence you don't want to compute this expression the way I've written it here explicitly. So formally I can write it like this and it's correct, but really to find XA you would solve the sparse system of equations that I've written further up. So I've not brought you images of what such Markov random fields look like, but you can produce some in the exercise, and I want to give you a few hints here. So how to simulate a Gaussian MRF, and here I'm assuming this is an unconditional simulation. So no conditioning on a observed subset of the variables. For simulation, we use the result that for a positive definite matrix Q, the Cholesky decomposition is unique. And the Cholesky decomposition it's what is colloquially known as it's more or less taking the square root of a matrix. So to sample from a normal distribution with covariance matrix Q minus 1, so we're only given the precision matrix, we do the following. So, in this notation here, normally you specify a normal distribution with its mean and its covariance matrix. And now rather than write the covariance matrix, I've used here the inverse precision matrix because I assume that you are given the precision matrix at the outset and you want to sample from the corresponding Gaussian process. So you can first do the Cholesky decomposition. So find a lower triangular matrix L so that Q is L transpose. And secondly, you take a standard normal sample Z. So just Z is going to be Gaussian white noise. And now you're going to color this Gaussian white noise by solving the following system here for X. Now you can verify that X does have the desired distribution because we can just check. So the covariance of X, the way we find X is going to be given by L transpose to the -1, which I'm writing here as L to the minus T times Z. Now I'm exploiting that the covariance of any matrix A times Z can be written as A times the covariance of Z times A transpose. So this is going to be L to the minus T times, well, the covariance of Z is just the identity matrix, because this is how we generated Z, times L to the minus 1. And if I take any matrix A times B to the minus 1, this is B to the minus 1 times A to the minus 1. So this is the same as L transpose to the minus 1, which is Q to the minus 1. So we've shown that X has a desired distribution because it has the correct covariance matrix and because it has mean 0. So Z had mean 0, and after this linear transformation here, it still has mean 0. Okay, so you can specify the precision matrix and sample from it or do other things. So to go back to the example I plotted last hour, that's a bad example because it has higher order interactions. So let's say if we were plotting time series, then I could use such a chain of random variables, and if I'm looking at the precision matrix here, let me try and draw it graphically. Okay. My precision matrix would be non-zero only in, okay, now it depends if I use periodic boundary conditions or not, but it would be, so the point is it would be a tri-diagonal matrix here. And the rest would all be 0. It's maybe a bit complicated picture to say what I've, if all I want to say is it's tri-diagonal. So all of this is 0. So I specify the interaction between a random variable and its neighbor, but because they are coupled and because they're jointly Gaussian, and because the precision matrix, because the covariance matrix is going to be dense, you will see that every random variable, so even one that's sitting here, will be correlated with any other, even those that are far away. But I only had to specify these interactions between neighbors in terms of the precision matrix. And by the way, if you now want to model long-range interactions, which is what we often want to do in image analysis, then we have to consider intrinsic Markov random fields, or nearly intrinsic ones.